Hi everyone, my name is Shohini Sarkar, and today I'll be presenting our work, Explainable Geospatial AI for Satellite Ground Station Sighting using LiDAR-Derived Terrain Intelligence. The main idea of this project is to improve how we estimate clutter height for satellite ground station planning. By clutter, I mean nearby obstacles like trees, buildings, or other structures that can affect radio signals. In satellite communication, these obstacles matter because they can change how signals travel, how inference is measured, and whether a location is actually a good place to put a ground station. Our goal is to move from rough fixed assumptions to a more accurate and explainable machine learning approach. To start, let's look at the current problem. In many RF planning workflows, engineers use standard clutter height values from the ITU recommendation. These are fixed values based on broad land categories. For example, open or rural areas are assigned around 0 to 10 meters. Suburban areas are assigned 10 meters. Urban areas, trees, and forests are assigned 15 meters. Dense urban areas are assigned 20 meters. These values are helpful because they are simple and standardized, but they are also very coarse. The issue is that two places with the same label can look completely different in real life. One suburban area might have short houses and very little tree cover. Another suburban area might have tall trees, dense housing, and much more clutter. If we treat both places as exactly 10 meters, we miss a lot of important local detail. That can lead to oversized exclusion zones, poor site ranking, wasted survey effort, and even interference risk if clutter is underestimated. This motivates the main shift in our work, moving from fixed rules to data-driven inference. On the left, we have the ITU baseline. It uses fixed categorical rules. The resolution is broad, and the mean absolute error is 4.67 meters. On the right, we have our light GBM model. Instead of using only a broadland class, it uses open satellite and geospatial data, with LiDAR-derived labels for training. The model predicts clutter height on a 100-meter grid. This gives a much more detailed view of the local environment. In our results, the mean absolute error drops from 4.67 meters to 1.79 meters. So instead of using one large conservative area, we can create a more realistic high-resolution estimate. Operationally, that means better site screening and more realistic coordination boundaries. A key part of this project is how we define the ground truth. We use LiDAR data from the USGS 3D elevation program. LiDAR gives us three-dimensional information about the ground and the objects above it. After processing and terrain normalizing the LiDAR data, we need to summarize each 100-meter grid cell with one clutter height value. We chose the 75th percentile of above-ground LiDAR heights. This choice is important. If we use the maximum height, the value can be too sensitive to noise or one unusual object. If we use the mean, the value can be too low in mixed areas, because many low points pull the average down. The 75th percentile is a good middle ground. It captures the dominant obstruction in the cell, but it is not as sensitive to outliers as the maximum. So our target is designed to represent the clutter that is actually meaningful for RF planning. Next, we build a feature stack using only open global data. This is important because we want the model to be useful beyond just the areas where LiDAR labels are available. The features include terrain and elevation data, such as Copernicus DEM, SRT-M DEM, slope, and aspect. We also include vegetation features like tree canopy cover and NDVI. These help the model understand natural clutter from trees and vegetation. For human-made clutter, we use population density and built surface information. We also include land cover data from ESA world cover, Copernicus land cover, and JRC forest type. Finally, we use Sentinel-2 spectral bands, plus thermal and emissivity data from master. The reason for using all these sources is that clutter is not caused by just one thing. Sometimes it is trees, sometimes it is buildings, sometimes it is a mix of vegetation, terrain, and human development. So the model needs multiple types of evidence to make a good prediction. We tested several model types, including ridge regression, random forest, a neural network, XGBoost, and Light GBM. Light GBM gave us the best overall balance of accuracy and efficiency. This makes sense for our problem. Our data is mostly tabular, with many different types of features. Some are continuous, like elevation or temperature. Others act more like categories, such as land cover class. Light GBM is well suited for this kind of mixed feature space. It can capture nonlinear patterns and feature interactions without needing a very large, deep learning model. Another major benefit is that light GBM works very well with SHAP analysis, which helps us explain the model's predictions. That matters because for engineering use, accuracy alone is not enough. We also need to understand why the model is making its predictions. This slide shows the full prediction pipeline. There are two main tracks. The top track creates the training labels. We start with USGS 3D EP LiDAR. Then we normalize the point clouds using PDAL, apply an IQR filter to remove unstable cells, and compute the 75th percentile cluster height target. The bottom track creates the input features. We gather global geospatial data like Copernicus DEM, Sentinel-2, WorldSpop, and ESA land cover. These are processed into features for each 100-meter grid cell. Then, the labels and features are combined to train the light GBM model. The final output is a continuous RCH prediction map. Instead of saying this whole area is suburban, so it gets 10 meters, the model gives a more detailed clutter estimate for each grid cell. Here are the main results. The ITU baseline has a mean absolute error of 4.67 meters. Our light GBM model reduces that to 1.79 meters. That is a more than 60% reduction in absolute error. The R-squared value also improves from 0.412 to 0.765. In plain terms, this means the model explains much more of the real variation in clutter height than the fixed ITU baseline. We also tested a no forest ablation, where forest and canopy features were removed. Even then, the model still had an R-squared of 0.617. This slide focuses on interpretability. We use SHAP analysis to understand which features are driving the model's predictions. The top feature is tree canopy cover, which makes sense. Tall, dense vegetation directly increases clutter height. The next important group is land cover information. This shows that the broad environmental context is still useful, even when we also have continuous features. Sentinel-2 spectral bands are also important. These bands help capture surface and vegetation patterns that may not be fully represented in simple map labels. This is a useful sanity check. The model is not behaving like a black box that learns random geographic shortcuts. It is relying on features that make physical sense. For a real engineering workflow, that is very important. If a site receives high clutter estimates, we want to be able to explain why. We also tested whether a more complex semantic segmentation model would improve performance. The segmentation masks look visually impressive, but when we added those features to the clutter model, they did not really improve performance. They also had very low SHAP importance, so we rejected them. This was an important design choice. A more complicated model is not automatically better. We cut the final pipeline simpler, more explainable, and easier to deploy globally. A major question is whether this model can generalize outside of the United States. The training labels come from US LiDAR, so we cannot claim perfect global validation yet. But we can test transferability using land cover matched international samples. Across the countries shown here, the model reached R-squared values from about 0.58 to 0.78, and it stays above the ITU baseline. This suggests that the model is learning environmental relationships that transfer beyond the original US training data. This matters because all the inference time features are globally available. So even though LiDAR labels are limited, the trained model can still be applied in other parts of the world. This is one of the main reasons we focused on open global data from the start. We also tested the model around deployed satellite gateway sites. The protocol sampled around 1,000 random points within a 100-kilometer radius of real gateway locations across the US, Hawaii, and Alaska. In this setting, the model achieved an aggregate R-squared of 0.68 and a mean absolute error of 1.9 meters. Certain sites performed especially well, like Hebron with an MAE of 0.3 meters and Grove City with an MAE of 0.45 meters. Some harder sites were places where the local environment was more mixed and heterogeneous. These areas had higher error, closer to around 4 meters. So where does clutter modeling actually pay off? First, spectrum coordination. More accurate clutter heights can help avoid overly conservative exclusion zones. That can potentially unlock spectrum access in areas that coarse models would mark as off-limits. Second, reduce survey burden. If we can screen sites better early on, fewer bad candidates need expensive field validation. Third, the biggest value may be in suburban and mixed environments. These are exactly the places where fixed categories often fail, because the real landscape is not purely rural, urban, or forest. Finally, better clutter estimates can support faster deployment. For large satellite networks, even small improvements in early filtering can save time, money, and engineering effort. This slide shows one possible application that we fleshed out. We started with around 11,000 candidate points, then we applied an RCH filter, excluding sites where predicted clutter was greater than 5 meters. After that, we ranked the remaining sites using other factors. These included population density, broadband coverage, and distance to population centers. The final output is a ranked list of the top 1,000 candidate sites. The key takeaway is that better RCH creates smarter filtering before expensive field surveys. It helps operators focus on the most promising locations earlier in the process. And this slide summarizes the full system. To wrap up, there are three main takeaways. First, there is a clear accuracy improvement. The light GBM model achieves 1.79 meters mean absolute error and an R squared of 0.765. That is a more than 60% reduction in absolute error compared to the ITU baseline. Second, the model is interpretable. SHAP analysis shows that it relies on physically meaningful features like canopy cover, land cover, and spectral signatures. Third, the model is globally deployable. The training labels come from US LiDAR, but all the features needed at inference time come from open global data products. Overall, this project shows that representative clutter height does not have to be treated as a fixed lookup table value. It can be estimated more accurately using interpretable geospatial AI. Thank you so much for listening. I'm excited about this work because it connects machine learning, remote sensing, and satellite communication in a way that is practical for real deployment workflows. I'm happy to answer questions. Feel free to reach out.